Okay, good day, everyone. I am Eric John Habel, and I am here to talk about a pulse amplitude modulation circuit design with LTSPICE simulation. So here is our Activity 5 Project 1. And we are tasked to design a pulse amplitude modulator circuit and an oscillator circuit. So the sine wave output of your oscillator will be an input signal to your pulse amplitude modulation circuit. And the oscillator must have an output frequency anywhere between 500 hertz to 3000 hertz. So the second is use LTSPICE or any similar software to provide circuit simulation of your design. So that's what we'll be doing. So we'll be using LTSPICE. So let's open LTSPICE here and open a new schematic. So here we have our finished pulse amplitude modulation circuit with a sine wave input. So here we have our 555 timer, 555 timer model, which is idealized as located in LT-SPICE as given. And here is a 10 voltage DC source. So it is connected to VCC and to RST, and its negative is to the ground, while both RST and VCC are interconnected with these two resistors and capacitor, which are all interconnected here. We used the 1N4007 diode 4007 for the high frequency of the digital wave that we are going to use. And so here is the output for this timer. So these are this digital wave and this sine wave are combined here to be pulse amplitude modulated. So we can clearly see that when we simulate that. So let's see, we can have a stop time at 5 milliseconds. Oh, okay, we haven't set yet the capacitor value for C at the top. So let's go ahead and set that to 10 microfarads. And let us run that. Here we have our output. So let me just fix some things first. So now I think it is fixed. So let's run it again. So here we have our analog wave, and here is our resultant digital wave. So let's first change that. So here is our modified pulse amplitude modulation circuit, and we can now simulate and check the result of a sine wave input of amplitude zero point 0.5 volts and a frequency of 500 hertz. So at a 5 millisecond time. So here we have our pulse amplitude modulated wave. And here it is in comparison to the analog signal. So we can see that there are juts coming up. So if we zoom for two of these cycles, you can see that the juts are inconsequential since they are almost uh, microseconds in, even picoseconds, I think. Yes, picoseconds in width. So we can disregard those lines going up and going down and just focus on the shape of the wave here. So as we can see, the analog wave is traced by the digital. So we can say that the signal is pulse amplitude modulated. So when we change the parameters of our sine wave input, let's see here, we change the frequency to, let's say, 1 kilohertz. And if we run that, we can see the wave like this, and we can see the pulse amplitude modulated wave there. So, I shown you the digital wave. So here is the digital wave. You can see that it has a high frequency compared to the wave, and that it has 0 as the lower voltage limit, and almost 1 as the 1 volt as the upper limit. So looking back at the uh, pulse amplitude modulated wave, we can see that it, let's remove first the digital because it's distracting. As we can see that the analog wave is traced by the pulse amplitude modulated wave. And if we change the frequency to the limit, so anywhere between 500 to 3000, so let's test for 3000 hertz. We run that. So here we have our sine wave, and here we have the modulated wave, amplitude modulated wave. And when you, let's we delete that trace, you can see that it is almost regular in pattern, but when we get it back, analog wave back, it is the same trace. It's still the same. But earlier I set the DC value, the amplitude of the sine wave to zero point 0.5 volts. What about if we, let's get back to the lower frequency, which is 500. If we set the amplitude to 1, we get a result of here. So here we have the pulse amplitude modulated output, which does not exactly trace the analog signal, since it's, you can see that its center is at negative zero point 0.4 volts. And yeah, and if you manipulate that, let's say the amplitude of the sine wave is just 0.25. So the lower the input sine, the amplitude of the sine wave input, the closer the pulse amplitude modulated signal will be to the outline of the analog wave. And if we manipulate our DC value here, so let's get that back to 1 volt. If we run it, you can see that it almost traces the wave perfectly. Well, it traced the positive half cycle perfectly, but the negative half cycle is not traced very well. Maybe if we increase the voltage, so manipulating the value again, you can see that it affects the digital wave. You can see its on state is more frequent than the off state. Let's get that back to 10, and let's see the waves. So what can we observe from that? We can observe that we lower the amplitude of the sine wave input, the more the pulse amplitude modulated signal will be closer to the outline of the analog signal. And the more we manipulate the value of this for VCC, we can see that the amplitude of the digital signal is manipulated. So that is our pulse amplitude modulated circuit design using an ideal 555 timer. And this is our oscillator input circuit. So yes, thank you for watching.